Chen from Shanghai Jiao Tong University. He will speak about almost optimal algorithms and other things.
Yeah, thank you very much for the introduction. Also, thanks for the organizer for inviting me here. So I will be talking about this result. It's mostly a joint work with Jörg Flum from Freiburg. So I guess 2 days ago, Albert gave a talk on some result connecting two main topics of this workshop. One is descriptive complexity, the other is proof complexity. So today I will also present you some result connecting these two areas. In fact, I will show you some open problems in these two areas are indeed equivalent. More than that, I will also show you these open problems are also equivalent to a problem in the third area, parameterized complexity. So to begin with, let me talk about these open problems so briefly. So first, this is an open problem in proof complexity. We know in proof complexity we study the length of various proofs of propositional tautologies in various proof systems. For instance, we are all familiar with resolution of Frege system or extended Frege. You can imagine there are infinite many proof systems. So ideally, we would like to have a optimal proof system in some sense. So more to be a bit more precise. So Koch and Rakow, also Kajacek and Pudlak ask whether we can have a proof system for tautology that can simulate any other proof system. So with a cost of with a polynomial cost. So depending on this strength of the simulation we are asking, we are looking for whether there is a p-optimal or polynomial optimal proof system or optimal proof system. I will define these notions more precisely later. So this is the first open question from proof complexity. So we know proof system more or less can be considered as a non-deterministic algorithm. So we are asking equivalently whether we have an optimal non-deterministic algorithm for tautology. So the similar question can be also asked for deterministic algorithm for tautology. So first, we can introduce a partial or pre-ordering on algorithms. Let's say we have two algorithms, A and B. So we say A is as fast as B, or A is less or equal to B. If for every alpha, so as a tautology, the running time of the first algorithm is bounded by a polynomial factor of the running time of the second algorithm B, so plus the length of alpha, because in some cases, some algorithm might decide the problem without looking through the whole instance. But here we emphasize this equality only holds on yes instances. So for this pre-ordering, Kajacek can also ask whether we have a minimal element of this pre-ordering. So namely, can we have an optimal, almost optimal algorithm for tautology? Here we are referring to deterministic algorithm. Also, by almost we are referring to the fact that we are only concerned with tautologies or yes instances. So this is the second open problem from algorithm concerning tautology. The third algorithm is exactly the central problem in descriptive complexity, which Albert, I guess, discussed in quite details 2 days ago. Here I want to present it in a slightly different form, which is most suitable for our purpose. So let's say we can have an effective enumeration of all polynomial time computable subsets of graph in terms of corresponding polynomial time machines. You can enumerate all Turing machines together with a polynomial clock to get such an enumeration. This should be very easy and straightforward to see. But the problem with such an enumeration is, so if imagine you have two graphs, G and H, they are isomorphic, but they have different representations. So it might well happen that in this enumeration, some of the machine MI might accept one of these graphs, G, but rejects another, the second graph, H. So this means that MI does not necessarily decide a class of graphs that are closed isomorphism. So here, a graph class closed under isomorphism is commonly known as a graph property. So we are interested in whether we can find enumerations of all polynomial time computable graph properties in terms of the corresponding Turing machines, polynomial time Turing machines. This is exactly the formulation by Chandra and Harel in their 1982 paper. But later it was known that this is equivalent to whether there is a logic for p-time, which is formulated by Gruvich in 1988. So this is the problem we have seen in Albert's talk, whether there is a logic for p-time. The fourth problem is a problem from parameterized complexity. Here we are concerned with the following halting problems. It's a very natural halting problem. So we are given a non-deterministic Turing machine M, and together with a natural number n in unary, so n many ones. So the parameter is M, the size of the machine. We want to know whether M accepts the empty importing at most n steps. So if you forget about the parameter, it's a standard classical NP-complete problem. So the question here is whether this problem is in the parameterized complexity class XP uni, slice-wise polynomial time, non-uniform version of this class. So, or more precisely, whether there is an algorithm deciding this problem in time n to the power of f of the size of m. So here f is a function. So if you fix an m, it's a polynomial. The point is, if you look at the brute force algorithm for this halting problem, you will see you require, so you need time something like the size of m to the power of m. The size of m to the power of n, sorry. So we are asking whether we can swap these two things. So this is a question studied. Oh, sorry, it's a typo. It should be hot. So this was a typo from the previous paper. We changed the name, sorry. It's a question first raised by Nash-Ramel and Viano, and later studied also by Ullman and Daub. So these are the four problems we will be talking about in this talk. So due to a series of results, starting from Krajcik and Pudlak and later Nash-Ramel and Viano, and also me and Froome, we now know these four things are equivalent. The first is there is a p-optimal propositional proof system, an optimal proof system. And the second, thought has an almost optimal algorithm, deterministic algorithm. The third, so LFP invariant, a logic introduced by Blas and Gruvich, captures p-time. And the third, the halting problem is in the class XP uni. So these four things are equivalent. Here I still haven't introduced this logic, but I will discuss this later. So you can see these four problems from four different questions turn out to be exactly the same problem. So this is the main result. But here I also want to mention that there is a further equivalent property concerning the listing of p-time subset of tautology due to Sadowski. But here I don't have time to discuss about this, but this property turns out to be very important in some of the proofs. So in the rest of my talk, I will first introduce or explain in detail, a little bit more detail, what is optimality for proof system and algorithm. Then I will talk about this equivalence between logic for p-time and optimality. And third, I will show you that this result can be extended to other complexity classes, and also they have some applications. First, optimality for proof system and algorithms. So I guess we have seen this definition of proof system introduced them by Cook and Rakow. So a proof system is simply a surjective function from finite strings to tautologies, onto function, which is computable in polynomial time. And the reason for introduce this very abstract notion of proof system perhaps is the following result. So Cook and Rakow show that NP equals co-NP if and only if taut has a so-called polynomial time, a polynomially bounded proof system P. So this polynomial bounded proof system means that if I have a proof W for a tautology alpha in my proof system P, then the length of this proof W is bounded by a polynomial of the length of the alpha. So this is a polynomial bounded proof system. Because of this equivalence, we now know there is this so-called Cook's program to separate NP from co-NP. So we want to show that there is no polynomial bounded proof system, and as a result, then NP is distinct from co-NP, which further implies NP is distinct from p-time. So this is the Cook's program. And as the first step, major step of this direction, we know that Hacken in 1985 proves that resolution is not a polynomial bounded proof system. Okay? But now we conjecture, because most of people believe NP is distinct from co-NP, so we believe both Frege and the extended Frege are not polynomially bounded. But so far, we don't have any progress on this direction. So This is the major open problem in proof complexity. But even if we prove this conjecture, we are still far away from separating NP from co-NP because they are simply infinite mini-proof systems. So we have to consider, we need to prove every possible proof system is not polynomially bounded. So that's the reason it's interesting to consider some kind of optimal proof system. So what is the optimal proof system? Optimal proof system, proof system P is optimal if for every proof system P prime, every other proof system P prime, and every proof W prime in P, I can find a proof W in P such that the length of the W is bounded by a polynomial of the length of W prime, and they prove the same thing. So in two different proof systems. So every proof in P prime, I can find another proof in P so that their lengths are not far away apart. So this is a...
The exponent depends exactly on P prime,
Yes.
yes?
And this is the optimal proof system. So if in addition, we can compute, so there is a polynomial time algorithm given W prime to compute the W, then this proof system is P optimal or polynomial optimal. So this has some additional algorithmic condition.
The condition missing that they are proving the same tautology?
Yeah, that's PW equals P prime W prime, yes. Thank you. And of course, we know there is an open question due to Krajicek and Pudlak whether there is an optimal proof system or even P-optimal proof system. So the advantage of having an optimal proof system is obvious. So if that's the case, then Cook's program boils down to one single proof system. We don't have to consider infinite mini-proof system anymore. Just look at this optimal one. But on the other hand, if there is no optimal proof system, also it brings some advantage. So we can show that every proof system has so-called easy to generate hard tautologies by a result due to Krajicek and later reproved by me, Flum, and Moritz. So I will explain this later in the end of my talk, what we mean by easy to generate hard tautologies. But at the moment, we don't even know whether Frege or extended Frege is optimal or P-optimal. So that's also an open problem. Now I explain what is optimal algorithm, which I already talked a little bit. So remember, we introduced a pre-ordering algorithm for tautology. So it means that for every tautology, the running time of the first algorithm is bounded by the running time of the second algorithm together with the length of the input within a polynomial factor. Okay. So an algorithm for taut, sorry.
Focus on yes instances.
So this is somehow related to the proof system because in proof system we are only concerned with yes instances. So it's only a technical reason to have this equivalence. Okay.
Just to remark, like everybody knows, if you only consider no instance, then you have an optimal exact. But
no.
Well, this Levin result, no. But could you explain it to or perhaps you,
no? Even for no instance, no instance is open.
But it depends on whether optimal proof system with respect to showing that that we have a satisfying assignment.
If so, an algorithm for taut, this Q should be taut, is almost optimal if for every algorithm B we have A is less or equal to B. So this is the minimal element in this pre-ordering. So one important remark is, which we will use later, is if A is an almost optimal algorithm for Q or for taut, and T is a subset of Q or taut, which is polynomial time decidable, then A has to run in polynomial time on this subset. So intuitively, it means that for almost optimal algorithm, if you have a set of easy instances, it has to be polynomial time on this set of easy instances. Okay? And also, we have some result concerning almost optimal algorithm. So Stockmeyer in his PhD thesis proves that every exponential time hard problem has no almost optimal algorithm. And the second, so this is an open problem from Krajicek and Pudlak for NP hard or co-NP hard problems. We don't know whether they have almost optimal algorithm.
As a curiosity, Stockmeyer, which terminology did he use?
I forgot it. It's quite obscure. It's not published, only in his thesis. So again, so if there is an almost optimal algorithm, so it gives you some advantage. So in that case, NP equals P time if and only if A runs in polynomial time on all tautologies. Okay. And the second, if there is no almost optimal algorithm, then by a result also due to me, Fluhman, and Moritz, every algorithm deciding taut, for every algorithm deciding taut, I can find a polynomial time computable mapping which maps every unary natural number n to a tautology alpha, so n, so that the running time of your algorithm A is super polynomial in I, so in n, hence super polynomial in the length of alpha I. So this means that every algorithm for taut has an easy to generate hard instances. Another way to put it is if a student claims that his algorithm solving set in polynomial time, then we can show him a set of well-structured or very easy to generate unsatisfiable formula to exhibit the super polynomial behavior of his algorithm.
Is this an effective? It's not an effective result.
It's not effective, but we know.
We can show him only if we are super smart, right?
Yeah, yeah, that's right. Okay, now I come to the main part of my talk, logics for p-time and optimality. So let me repeat the question of Chandra Hare again. So first, remember a graph property K is a class of graphs such that it's closed under isomorphism. Namely, if you have a graph G in K and another graph H is isomorphic to G, then you have H also in K. And Chandra and Harel's question is whether you can effectively enumerate all polynomial time computable graph properties by exhibiting a corresponding polynomial time machines that decide these classes. Okay. But to formulate this problem in more a logic fashion, so we need a notion of abstract logics from model theory. So here it's a very general notion of logic. So a logic L consists of a recursive set of sentences. So think about FO sentences, list of fixed point logic sentences, second order logic sentences. This is the syntax part of the logic. For the semantics, so we need a satisfaction relation, so which determine whether a graph G satisfies an L sentence. So G is a model of phi. Here I restrict myself to graphs. Of course, you can talk about general finite structures. So what is also important is for every pair of isomorphic graphs G and H, G is a model of phi if and only if H is a model of phi. So in logic, you cannot distinguish isomorphic graphs. So think about L as a programming language, and phi is an L program whose input are always graphs, and the output are always yes or no, and this program cannot distinguish between isomorphic graphs. So what is the logic capture p-time? So in this notion of, for this abstract notion of logic. So we say L captures p-time if every polynomial time decidable graph property can be defined by a formula from this logic. So every p-time property can be defined in your logic. And the second, we need to have an algorithm A, so this model checking algorithm, which decides this satisfaction relation of L in such a way that for every fixed formula, phi, the algorithm has to run in polynomial time on the size of the graph G. So this is the notion of logic capture p-time. So we know this famous Immermann and Vardy theorem that we have effective enumeration of ordered graph properties in p-time in terms of corresponding polynomial time machines, or more precisely, the least fixed point logic captures p-time on ordered graphs. So the problem is, compared to the previous notion here, we are talking about graphs together with a built-in order. But for the previous definition, we are only given a graph without an ordering on the vertices. Okay. So what is the logic LFP? So we talk about this, it's equivalent to inflation fixed point logic. So you can think about LFP as an extension of first order logic by least fixed point operators. In fact, for our result, we don't really need any particular property of least fixed point logic other than it captures p-time on ordered graphs. So LFP, you can think about this as a programming language whose programs are exactly those polynomial time algorithms. But the thing is, as usual practice in programming, so if you are talking about import as graphs, these graphs always stored by, say, its adjacency matrix or its adjacency list. So in any case, the graph comes with a built-in order. So the vertices are ordered. So if you think of it like this way, so you are always concerned with graphs together with an ordering, always. So we can write an LFP sentence. So in that case, to express even in FO sentence, there is an edge between the first and the third vertex in the graph. Okay? But this is, of course, not a graph property because you can think about two graphs. So one graph together with two different ordering, one satisfies this property, the other does not. So this is not a graph property. What we are aiming for is those properties that are invariant under all possible ordering of the vertices. So that's the main problem with LFP. So this motivates the following notion of order invariance. An LFP sentence phi is order invariant for all graphs G. Order invariant if for all graphs G, so I miss an if. For all graph G and all ordering, so all two orderings, the first less 1 and the less 2, we have G together with the first ordering is a model of phi, if only if G together with the second ordering is a model of phi. This means that the validity of phi in G does not depend on the way how we store G in our memory. But this property is undecidable. It should be very easy to see. And as a result, we cannot take this set of sentences as a logic. So phi is an LFP sentence, phi is order invariant. This does not form a recursive set, so we cannot take this as a logic. So this then Blas and Gruwich has this very nice idea to restrict this order invariance to some initial segment of the natural numbers. So we say LFP formula phi together with a natural number n, phi is less or equal to n invariant if for all graph G of size at most n, so containing at most n vertices, and all two orderings less 1 and less 2, we have this equivalence. The difference is now we are looking at the graphs of a certain size, not all possible finite graphs. So clearly this is decidable because we can simply enumerate all possible graphs. As an example, we can see there are even number of vertices is less or equal n invariant for every n. In fact, it's order invariant. So the second property, if the graph contains at least 100 vertices, then there is an edge between the first and the 100th vertices. It's less than equal to 1, less than equal to 2, up to less than equal to 99 invariant, but not less than equal to n invariant for every n at least 100. To see the first, so it's simple because the premise is violated in case G contains less than 100 vertices. So this is an example which is less or equal to n invariant for some n, but not order invariant. From this, I define a binary relation invariant which consists of all tuples phi n, so that phi is a LFP sentences and n is a natural number, so that phi is less or equal to n invariant. So now we can define this LFP invariant logic. So LFP invariant has exactly the same syntax as LFP, so they have the same sentences. And the semantics is a bit different. So we are given a graph G. We want to decide whether G is a model of phi. So from this LFP invariant logic, this is equivalent to say that G together with the size of the graph is in this invariant relation, namely, so it says that phi is less or equal to the size of G invariant, and together with the condition that G together with an ordering, so this is an ordered version of G, is a model of phi. But here this order can be any ordering or one of the ordering of this graph, because we already know by the first condition phi is less or equal to the size of G invariant. So which order you choose doesn't really matter for the second condition. Okay.
The complexity of checking for the users satisfies phi, even for fixed phi is no longer polynomial time. To check whether the pair phi size of G is invariant, you have to look at all graphs up to the size of G.
It's not polynomial time, yeah.
It can be complete even for fixed phi.
Yeah, Hamiltonian passes. Yeah. Yeah.
It is.
Okay. So again, let's see an example. So let's define the formula phi is as if the graph contains at least 100 vertices, then there's an edge between first and 100 vertices. So I already mentioned that phi is less or equal to n invariant if and only if n is a number at most 99. So as a result, G is a model of phi if and only if G contains at most 199 vertices. Okay.
What if G is the complete graph?
But the condition is that the graph contains at least 100 vertices.
Right, so take the complete graph on 100.
Yeah, then the first condition is violated because here I'm not talking about the graph G itself, I'm talking about all the graph of size up to the size of G. So even if you are a complete graph, you can talk about it. Okay. So the question is whether LFP invariant captures P time. It's not very difficult to show that for any class of graph K, K is in P time if and only if I can find a sentence phi from this logic so that K.
I'm a little confused because the discussion we just had showed that even the first part is now is NP power. Just checking in. It's already checking satisfaction has to be for any fixed phi has to be in polynomial time, right?
Oh, sorry, that's wrong. So it's not co-NP, it's in P time in fact, because so for the fixed phi. There are only two cases. Phi is order invariant. And another case, phi is not order invariant. Then you have, for the first case, you have all n inside. For the second case, you have a minimal I, so that phi is not less or equal to I invariant, but it's phi is less or equal to I minus 1 invariant. In that case, you have a finite set.
Yeah, but that's still okay. So there's two separate questions. So for any fixed phi, the class of graphs that satisfies it is polynomial time.
Yeah.
But part of the definition of there's a logic for P is that you can effectively translate from phi to a polynomial time machine.
No. There is no such condition in the logic.
Just effective enumerability.
Yeah. There is no effect.
But in Gurevich's definition, that was...
This was Gorevich's definition, but not Chandra.
No, that's right.
Gorevich wanted uniformity, but Chandarel did not require uniformity.
Okay, so the simple observation is K is in P time if and only if you can find such a phi to define it in our logic.
I think the discussion, it's not clear that you are using really the original Gorevich definition, but when you look at capture.
Yeah.
Because I think he did wanted uniformity.
Yeah. He required that as an effective translation from formula to a polynomial machine. That was part of the Gorevich.
So this is a modified version of capture.
Okay. Yeah. So remember, we have these two conditions. The lemma says the first condition is satisfied. So then the first question, whether LFP invariant captures P time, is equivalent to the question whether there is an algorithm deciding this invariant condition phi n in such a way that for every fixed phi, the algorithm A runs in time n a polynomial of n. So this would be the condition we are talking about. So the main result of our theorem is taught as an almost optimal algorithm if and only if LFP invariant captures P time. And in the light of the previous observation, we recall that phi in LFP invariant and every graph G is a model of phi if and only if the first thing is phi, the size of the G is in this invariant relation, and the G together with an ordering is a model of phi. So the theorem can be restated as taught as an almost optimal algorithm if and only if there is an algorithm A deciding phi n in invariant, whether it's a member of this invariant relation, in such a way that for every fixed phi, the algorithm A runs in polynomial time with respect to n. Okay. So how to prove this? So how to use optimality to achieve this algorithm? So let's assume that taught has an almost optimal algorithm. So our goal is to construct an algorithm deciding phi n, whether it's a member of invariant relation, in such a way that A runs in polynomial time for fixed phi. Now remember the definition of phi n in invariant. So phi is less or equal to n invariant if for all graphs G with the size of G bounded by n and all orderings less 1 and less 2 on G, we have the equivalence between G together with the first ordering is a model of phi if and only if G together with the second ordering is a model of phi. So as here you can see, this is a universal condition. So for all graphs G and for all orderings. So it's very easy to turn this into a co-NP condition by padding some additional numbers. So we are looking at the following problem Q, which consists of all tuples phi n together with n to the power of phi minus 1, so that phi n is a member of invariant relation. Here I need these additional ones to guarantee I have sufficient time to check these conditions. So this gives you sufficient time to check whether G together with an ordering is a model of phi in polynomial time. So because phi is a co-NP complete, there is a polynomial time reduction from alpha from Q to tautology. So which maps every tuple phi n together with some ones to the formula alpha phi n and ones. So of course also we need the standard padding technique so that once we are given this instance produced by the reduction, we can recover phi n n. So this would be needed in our proof. So now let's fix a formula phi from this logic. So we consider the following set Q of phi, which consists of all the instances produced by this reduction, so that n is a natural number and phi n is in our invariance relation. It's clear this has to be a subset of taut because I require this phi n is a yes instance and alpha is a reduction from yes instance to tautologies. Now let's say that phi n is invariant for all n. So this says that phi is really order invariant. And remember, by padding we can recover phi n from alpha phi n from this instance produced by the reduction. So in polynomial time or even in log space. As a result, we can see that this set Q phi is in P time because I can recover phi n n. And in fact, we fix this phi. Now let's say that we have an almost optimal algorithm O for taut. Then by the optimality, O accept the set Q phi in polynomial time. Remember, when we introduced this notion of almost optimal algorithm, we say that if there's a subset, polynomial time subset of this tautology, then this optimal algorithm has to run in polynomial time on this subset too. So this is the reason here we say we can conclude O accept this set Q phi in polynomial time. Now I turn this optimal algorithm into the following algorithm B1. So this algorithm on every instance phi n computes this alpha phi n, so compute this reduction. And then I simulate this almost optimal algorithm O on the produced instance by this reduction. Now if I look at all those phi n, so remember I fixed the phi and phi n is invariant for all n. So B1 accepts all these phi n in time n to the power of phi at the length of phi of some polynomial. Here n to the power of phi comes from the fact that I have to pad some additional ones. But remember, I said that O has to accept this set in polynomial time. This comes to the polynomial factor here. So all in all, because phi is fixed, it's a polynomial in n. So in case phi is order invariant, I have an algorithm runs in polynomial time on this phi n. Okay? So this is one direction, so one side of this phi. For another case, phi is not order invariant. So this means that phi n is not in this invariant relation for some n. Then of course there is a graph G with size at most n and two orderings less 1 and less 2 on G, so that together with the first ordering, G is a model of phi, but with the second it's not a model of phi. So this witness the fact that phi is not order invariant. Then we can consider the second algorithm B2, which on every instance phi n. So the first step is brute forcefully check for every I from 1, 2, 3, and so on, every graph G and every two ordering less 1 and less 2, So here I need the size of G is bounded by I. Whether G less 1 is model of phi, if and only if G less 2 is a model of phi. Once I find this equivalence doesn't hold, I will stop. So essentially, the first step is to look for the first I to witness phi is not order invariant. So if that's the case, I find this I, then I check whether the given n is less than I or not. If that's the case, then accept, because I is the minimum number to witness phi n is not invariant. So if n is less than I, then phi n is order invariant. Okay? Otherwise, it rejects. So the second algorithm goes like this. So remember, here I assume phi n is not invariant for some n. So phi is not order invariant. So this implies that the step 1 eventually halts with the minimal I with phi n is not invariant. And we get the correct answer from the second step. And the learning time by B2 on this instances phi n only depends on, the first step of this B2 only depends on phi because it has nothing to do with n. And by fixing this phi, I know this B2 need time only polynomial in n. So in case phi is not order invariant. So you can see we have two algorithms, one dealing with order invariant phi, the second one dealing with the not order invariant phi. Now back to our goal. So our goal is to find an algorithm deciding this relation in such a way that for fixed phi, the algorithm runs in polynomial time with respect to n. Now it's simple by simulating both algorithms B1 and B2 simultaneously. And if one of the simulation halts, then I will accept or reject according to the halted simulation. So it's easy to see that this gives you the desired algorithm. So this desired A. Okay. So this shows that how optimality implies logic capturing. So for another direction, I can only sketch the proof very briefly. So how you go from logic capturing p time to optimality. So imagine, so first thing, so this is in fact a wrong proof, but this gives you the idea. Imagine there were an effective enumeration of all proof system P1, P2, and so on, which is generated by an algorithm A. So A generates all possible proof systems. But of course, we know this is impossible. But if that's the case, then we would have an generate the code, the program.
Generate the code.
Yeah. Then I can define a P optimal proof system P in the following way. So P accepts 4 parameters, I, C1, W, C2. It will output PIW in case I is a natural number, one of these. And the C1 is the computation of A on I, which generates PI. And the third, C2 is the computation of PI on W. So altogether, you can see P is polynomial time computable, and moreover, every proof system, because you enumerate all of them, can be simulated by P in polynomial time by a polynomial translation. But of course, this is not correct because we don't have any way. So it's no way, there's no way you can generate all proof system. It's undecidable whether a function is a proof system. So then the idea would be slightly relax this enumeration and adding some further conditions to check whether the enumeration gives you some correct answer. So of course, we have effective enumeration of all functions, A1, A2, from sigma star to sigma star. And here should be computable functions. Yeah. And then I define a proof system which, similar to the previous case, PI C1 W C2 equals AIW, where, so here is something very rough. So C1 is a proof of the fact that AI maps every string of length at most the length of W to a tautology. So this would be the way we can turn effective enumeration for not necessary proof system to a proof system that only maps strings to tautologies. But here I have no time to explain what we mean by a proof. And if for every y such C1, so such proof, if it exists, can be found in time the length of W to the power of some function of I, then P can be shown to be P optimal. But of course, I have to explain what we mean by proof. But I only say that this can be achieved in case this halting problem is in XP uni. So in fact, this problem can be easily turned into a problem which is quite similar to halting problem. Okay, so now comes to the last part of my talk. I want to explain how to extend this result. We are always talking about proof system logic for p-time. Can we do something different also? Can we generalize this to other things? The first thing I want to talk about is these non-deterministic versions of our result. I guess in proof complexity, this optimal proof system perhaps is more interesting than p-optimal proof system. But for this, we can prove the following equivalence. So there is an optimal propositional proof system. Here, we don't require that there is a polynomial time algorithm to translate every proof in one proof system to your optimal proof system. Only I require that there exists a proof in the optimal proof system that is not very far away from. The length of the proof is not far away from the length of the proof in the proof system I want to simulate. So this is an optimal propositional proof system. This would be equivalent to thought has an almost optimal non-deterministic algorithm. Okay. I guess the definition is similar in the case to the case of the deterministic algorithm by requiring the running time to satisfy some inequalities. And what is important is the third property. So the third property states that there is a non-deterministic algorithm that decides the following variant of this halting problem in time n to the f of the length of m for a function f. Here we require it's a non-deterministic algorithm. Compared to the previous case, we require it's a deterministic algorithm. But here the problem is slightly different from the previous halting problem. The input is the same, a non-deterministic machine m and a natural number n in unary. But the problem becomes, I want to decide whether every accepting run of m on the empty input take more than n steps. So it's a kind of complement of the previous problem. The main point is I want to have this problem in co-MP, so which is in line with tautology. Tautology is a co-MP problem. But I don't have time to explain this, but just to emphasize we have a halting problem corresponding to, a conditional halting problem corresponding to optimal proof systems. Another extension concerns log space versions. Messner and Toren introduced this notion of log space proof system. So it's similar to the standard proof system, which is a surjective function mapping finite strings to tautologies, onto tautologies. But here I require this function to be computable in log space. I guess most natural proof systems are in fact log space proof systems. So a log space proof system for tautology is space optimal if for every log space proof system P prime for taut, there exists a log space computable function which maps every proof from the second proof system to the first proof system. Okay. The thing is, I need this translation to be computable in log space instead of polynomial time in case of optimal proof system, p-optimal proof system, sorry. So for the corresponding notion for deterministic algorithm, an algorithm A deciding taut is almost the space optimal if for every algorithm B which decide taut there is a constant D, and for every tautology alpha I have this inequality which bounds the space required by the optimal algorithm A in terms of the second algorithm B, so together with logarithmic of the length of alpha. Okay. What we can show in this direction is the following are equivalent. There is a space optimal propositional log space proof system. Taut has an almost space optimal algorithm. This deterministic transitive closure logic invariance version of DTC captures log space. So this shows we can translate all the result to the log space area. Okay. So all the equivalence we have seen for non-deterministic log space or polynomial time are only equivalence. Can we really use this equivalence to say something about, say, proof system or logic for p-time? Here is the result we can really prove. So of course, we need some complexity assumptions. So this concerns so-called effective version of these proof systems. So remember, a proof system is p-optimal if for every proof system I have a polynomial time translation. So transfer every proof in the second proof system to the first proof system. If we can compute such a translation from the second proof system, from P prime to T. Then we say we have effectively P-optimal proof system. Okay? So to have an intuition about this notion, just think about Cook's completeness, set completeness. In fact, he shows that if you have a problem and you are given a machine, NP machine that decides this problem, you can compute from this code of this machine a reduction from this problem to set. So here is something similar. I need to compute this translation from the code of the second proof system. So that would be the effective notion of P-optimality. So for the logic side, we can also say LFP invariant effectively capture P time if there is an algorithm A which decides whether G satisfies in time the size of G to the power of f of the size of phi, here for computable function f. So originally we don't have this computability condition. Here I require f to be computable. But the bad thing is we don't really know whether these two things are equivalent. There is an effective P-optimal proof system if and only if LFP environment effectively captures P time, because due to some very strange or subtle technical conditions. Nevertheless, we can prove these things don't really exist, assuming some complexity assumptions. Here, we need an assumption what we call NPTC is not contained in NPTC log TC. Here, TC refers to time constructible functions. This means that for every time constructible and increasing function h, n time polynomial of h is not contained in d time h to the power of O log h. So think about h as an identity function. This will tell you NP is not contained in d time n to the log n, O log n. So more or less it says that NP is not in quasi-polynomial time. But here, of course, it's a very further generalizations concerns all time constructible functions.
The second NP is probably P.
Yes. Sorry. Thank you. Thank you very much. So for this assumption, we in fact are able to link this to some known assumption from Jack Luz from 1997. So he formulated this assumption using his resource bounded measure. NP does not have measure 0 in EXP, then our assumption holds. Sorry, this should be P, so it's a macro error. So under this assumption, NP is not contained in PTC log TC. There is no effective P-optimal proof system for taut LFP invariant does not effectively capture P times. So these are the things we can prove, of course, assuming some complexity assumptions by exploiting this equivalence we established. So finally, I want to say something about hard instance for algorithms using our results. Let's say we have an algorithm for taut that does not run in polynomial time. Of course, we know then there must be a sequence of instances, alpha 1, alpha 2, alpha s, so that the running time of your algorithm A is super polynomial in the length of alpha s. So this simply follows from this assumption. But as in many results in complexity theory, we are not only interested in the existence of these objects, we want to find whether we can generate such instances efficiently. Okay. So this motivates the following notion of hard sequence for algorithm. So let A be an algorithm for taut. A sequence alpha s is hard for A if every alpha s is a tautology. So alpha s is a yes instance, and the second, this sequence can be computed in polynomial time given this s in unary. And last, the running time of of A on this instance is not polynomially bounded in S or super polynomial in S, because alpha s can be computed from one s in polynomial time. This implies this running time is not polynomially bounded by alpha, the length of alpha s2. So this would say that I can generate a sequence of instances to witness the super polynomial time behavior of your algorithm. Okay. So using our equivalence, we can prove If tot has no almost optimal algorithm, then every algorithm for tot has a hard sequence. The proof is in fact quite easy once you have this equivalence. So we just look at this halting problem. So an NT MM and M in unary, we want to decide whether the run of M on every input take more than n steps. So we know this problem is not in XP unit if and only if tot has no almost optimal algorithm. And it's also a very easy exercise to see that this is equivalent to say that for every algorithm H deciding this problem, there is a non-halting machine M, so that the running time of your algorithm on this instance M1n is superpolynomial in n. And then I can turn this into a hard instance for your algorithm H for tot. Because this problem, remember I turn this p hot less or equal to p hot greater, which is essentially is a co-NP problem. And there's a reduction from this co-NP problem to tot. And I can compose any algorithm for tot together with this reduction to get an algorithm for this co-NP problem hot greater. And then by a simple calculation, you will see that I guess I have so much time. So you can see that the algorithm deciding tot together with this reduction. So this gives you an algorithm deciding p hot on these instances Pn1n, which is the sum of the running time of your reduction and the running time of your A on the instance produced by reduction is superpolynomial in n. But as a result, Rm1n, this instance produced by reduction, is a tautology because M is a non-halting. And the second, the running time of your algorithm A on the instance produced by the reduction is superpolynomial in n, because R is a polynomial time reduction. And altogether, we can see the instances produced by your reduction on all M1n. Remember, M is a fixed non-halting machine. This gives you a hard instance for your algorithm A. Okay. So finally, I want to say this hard instance for proof system. Again, so we can motivate this by the following things. So let's say P is a proof system for tot that is not polynomially bounded. Then, of course, there exists a sequence of tautology alpha 1, alpha 2, and alpha s, and so on, so that the length of a shortest proof for alpha s in our proof system P is superpolynomial in the length of alpha s. Okay. The question is, can we generate such a hard sequence alpha s efficiently? This is also something we want to have because imagine we want to prove Frege is not polynomially bounded. So it may well happen that you have instances to witness this superpolynomial bound of your Frege, but they are really hard to find. You have no way to exhibit such instances. So explicitly or by some algorithm, by writing down some simple argument, then this would be very bad. So you can hardly argue that. Okay. This also, you can think about Haken's result. Pigeonhole principle is hard for resolution. In fact, pigeonhole principle is some kind of instance you can produce in polynomial time. But this witnessed the superpolynomial behavior of your resolution proof system. So this is the thing we are looking for. So let's P be a proof system for tot. Our sequence is hard for P. Again, a sequence of instances alpha s. So if every alpha s first is a tautology, so we want to prove it's a tautology in our system P. And second, we can produce these instances very efficiently in polynomial time. And lastly, the length of a shortest proof alpha s for alpha s in our proof system P is not polynomial bounded in S, has not polynomially bounded in alpha s. So we can prove that if tot has no optimal proof system, then every proof system for tot has a hard sequence. This is in fact a result proved by Krajicek, and his result in fact is much stronger without assuming there's no optimal proof system. His assumption is only if P is not an optimal proof system, then it's not optimal, then I can find such a hard sequence. But we proved this result, a weak version, using completely different manner, so using our equivalence. So the idea would be using the equivalence I mentioned in some of the previous slides. So the equivalence between there is no optimal proof system there is no non-deterministic algorithm that decide this halting problem in time n to the power of f of the length of n for the function f. Using the previous technique we used to prove there is a hard sequence for every deterministic algorithm. Okay. So here are some references. I guess I stop here. Thank you.
Thank you for this very clear talk. Questions, remarks?
So I think it's a very nice connection between connecting kind of different questions in complexity theory. I'm not sure you use just the right definition of Gurevich. I think that this definition is somewhere between Gurevich require, as I recall, uniformity, and between Chandra and Ariel that require less.
Yeah, but essentially, I think Gurevich in his paper showed that if you take the Chandra and Hara without uniformity, then there is a positive answer just by taking something like this. You take all polynomials and you try and vary it by two. And that's why he added the uniformity condition. So in some sense he showed that without it, there was a trivial answer.
Here we're not using uniformity.
No, it did appear.
Uniformity? Well, later, effective.
Effective
was the
it's a
uniformity,
different
but until that point there was no uniformity.
The uniformity is one-sided here.
Effective is a uniformity condition, but before that there was no uniformity.
Okay. Where is it?
The effective version, I think it's corresponding to uniformity.
Go forward.
I think the second condition is a one-sided uniformity.
There's another with decisive satisfaction in such a way that for every fixed. Yeah, so there's a single algorithm. This is the
There is an
uniformity.
algorithm.
Yes.
So what's the algorithm for checking invariant?
What do you mean by?
Invariance, I mean, we have to check that this meets your algorithm, the
No, it
loop
doesn't.
condition.
It doesn't. That's why it's still a question, right?
Yeah, it's still open.
No. But the condition, in the definition, there was in definition
yeah.
here, right?
And that's why LFP int, whether it meets that definition is an open question because we don't know that there is such an algorithm.
So I've yet to be convinced that when we say here that the theorem that talks about LFP int captures p time, that this is the Gurevich norm.
Just go on to the next slide. I think there's a question: does LFP int capture p time? And basically, if there is an algorithm which decides in, then it does. Because if there's an algorithm that decides in, you get the uniform.
That algorithm follows.
Yeah.
And what's the answer to that?
No, we don't know.
Perhaps, so there's another of Jan.
Yeah, but does it mean that if there is a logic for p time, then LFP invariant is a logic?
No, this we don't know. So there might be another logic captured p time.
But you have this open problem, and you say if this
No,
is true,
so
then LFP
the first. Oh, sorry. Here it's the third point is not referring to any logic. It's a specific logic. But in fact, we can say there's a logic. I can replace LFP invariant by any logic, but I have to strengthen a little bit this captured p time. I have to strengthen captured p time on any co-NP classes of graphs. But this is something very technical.
Perhaps the last question by Jan.
So do you think the answer to this problem is yes or no?
I would believe no.
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 Okay, so then let's thank the speaker again.